Now looking at PB, which is the bit pressure drop, well, basically the pressure drop across the bit can be worked out using this equation here. PB equals density times the square of the flow rate divided by 10,858, and also divided by the square of the total flow area of the bit, where basically you've got rho in this equation, fluid density in pound per gallon, Q is flow rate in gallons per minute, and TFA is in square inches as well. Otherwise that constant changes. That was a bit pressure drop equation. You can also work out what is the available bit pressure drop. So you can then work out what jets you could actually put on your bit without blowing the pop-offs on the standpipe pressure. I mean, mainly what we're looking at here is, remember, PC was your total circulating pressure, or your standpipe pressure. There's going to be a maximum value to that, and that's the maximum output of the pumps. And usually, you know, your pump manufacturer will give you a value that's the maximum pressure that the pumps can hold. And in general, I'd say most drilling engineers, when they're designing the overall wellbore, would only really want to go to about 80% of the maximum standpipe pressure. Certainly the guys on the rig would only want to go to about 80% of the maximum standpipe pressure. So that would be your limiting factor. So you can work out, you know your pipe diameters and your IDs and ODs, so you can work out all these pressures, and then you know what your maximum standpipe pressure is, the maximum you want to go to, and therefore you can back calculate what your bit pressure drop, your available bit pressure drop actually is. So whatever's left, you can nozzle down, you can reduce your nozzle size to increase this pressure drop to the maximum value in that equation. And we can basically find the required nozzle velocity in feet per second, and then back calculate the optimum TFA required to maximize the pressure drop at the bit. Now, the nozzle velocity in feet per second is given by this equation, which is your available bit pressure drop divided by the density of the mud, and that get the square root of that. And the TFA can then be back calculated using this equation. It's 0.32 times the flow rate over that nozzle velocity that you've just worked out. And then that will give you your TFA, and then you can simply work out what nozzles would be required to give that TFA. And that totally depends on how many nozzles you can screw into the bit, which could be 3 for a rock bit, maybe 4 if it's got a center jet, 6, 7, 8, whatever, depending on what type of bit you're running. Now, when we're actually optimizing bit hydraulics, we're attempting to accomplish two things. And we're wanting to actually maximize the penetration rate by efficiently cleaning cuttings from the face of the bit. And we're also wanting to prolong the bit life through cooling of the bit as well. Now, before we talk about bit hydraulics, we really have to work out in our heads what nozzle flow is all about. And the best way to demonstrate that is by looking at a garden hose. Now, if I've got a garden hose here and I've screwed the nozzle on the end completely shut, you've got you've got no flow coming out of the end of that garden hose. If I now open the nozzle a little, you start off with you end up with some water and some cleaning power. So when it was closed, there was no cleaning power whatsoever. Now you've opened it a little, you've got a spray coming out, and you've got some cleaning power. If you open it some more, you now have a nice jet coming out, and you've got an optimum jet of water and optimum cleaning power here. But if you continue to open that nozzle, then what happens is it gets too wide, and that optimum jet, that optimum flow rate's passed, and you end up with a trickle of water, a lot of flow coming out, but it's not got any cleaning power. So there's an optimum point at which you can adjust that nozzle size, or the TFA basically. So at this stage we've got very little power in the jet, but we've got maximum flow. So somewhere along that opening up of the TFA and increasing the flow through there was the optimum point at which you were achieving cleaning. So we can actually graph that and say, right, Looking at this, we've got flow along the x-axis, we've got cleaning power, we'll just call it at the moment, up the y-axis. And as we opened the nozzle of that garden hose, we got up to an optimum point. And then beyond that, the flow continued to increase, but the cleaning power decreased. Now, if we apply this graph to a bit and have a look at hydraulic horsepower on the y-axis, and flow rate in gallons per minute on the x-axis, and TFA in square inches on the x-axis as well, just putting it on the same sort of scale. If we go from 0 TFA to completely open jets, and 0 gallons per minute to, say, 700 gallons per minute, somewhere along here, perhaps about 500 and something gallons per minute, would have been the optimum TFA, allowing that flow rate and giving them, maximizing your hydraulic horsepower. So there's a point at which you maximize that hydraulic horsepower, and that's you getting the optimum cleaning power at the bit. Your energy that you're inputting at surface is being basically you're using the maximum amount of it to clean the bit at the bottom of the hole if you were to optimize this. So basically the input of hydraulic horsepower from the engines is converted to flow rate and pressure at the mud pump. And some of this power is actually reconverted into output hydraulic horsepower at the bit. And the hydraulic horsepower is the rate at which the fluid does work. If you remember back to the definition of energy, or work rather, it's basically then the rate at which it actually applies energy. And that's measured at the flow area of the bit, or basically the nozzle orifices. So the hydraulic horsepower, for the bit hydraulic horsepower is measured at the nozzles of the bit. And any loss in power is due to the consumption of energy due to friction. As we know, we need pressure to pump it down to the bit, so some of that energy that you're inputting at surface is lost before it gets to the bit. So there's only a certain amount of hydraulic horsepower left to actually clean the bit compared to what there was at the surface. Now, the other way of expressing this hydraulic horsepower, when I say it's applied at the nozzle orifices, you could also express it as HSI, or hydraulic horsepower per square inch. If you divide the hydraulic horsepower by the TFA of the bit, you end up with hydraulic horsepower per square inch. Now, there is another term in bit hydraulics called impact force, and it's defined as the rate of change of fluid momentum through the bit as a function of the fluid density, flow rate, and nozzle velocity. And these are all things that we can calculate as well. And we can optimize the impact force. I'll show you a little bit about that in a minute. Now, adjustment of hydraulic parameters to maximize the ROP boils down to basically maximizing the hydraulic horsepower at the expense of flow rate, or maximizing the flow rate at the expense of hydraulic horsepower. The choice depends on some of the following factors, and you've got bit type, mud type, rock strength, and rock characteristics as well, as in how hard it is and how friable it is, how easily broken it is as well. Now, roller cone optimization is generally achieved by maximizing the hydraulic horsepower, although sometimes optimizing the flow is better. Now, flow rate needs to be maintained at, as a rule of thumb, greater than, say, 50 gallons per minute per inch of bit diameter for good hole cleaning and wellbore integrity, no fluid loss. That's just a rule of thumb, not something you would apply, but something you can have in your head, just to give you a reasonable gauge of what your flow rate should be to clean a hole. About 50 gallons per minute or more per inch of bit diameter. Now, within that sort of limit, the nozzles should be calculated to give 65% of the system pressure loss at the bit, and that's also limited by the maximum standpipe pressure allowable as well. So within these constraints, if you can choose the correct nozzles to give you 65% of your total system pressure loss, or your total standpipe pressure at the bit, then you're going to have optimized your hydraulic horsepower and optimized your cleaning of the bit in the bottom of the hole. Now, maximizing impact force is also considered optimum for hole cleaning, but in this case the impact force in PSI should be equal to 48% of the system pressure loss. So in reality, what we see is a graph with two optimum flow rates and TFAs. If you've got flow rate, and you could have TFA along the top of here as well, You've got hydraulic horsepower in horsepower, basically, and impact force in pounds. If you were to plot these on a graph, you've got hydraulic horsepower and impact force both being graphed together, and you've got two different optima. This is your hydraulic horsepower here. This is your impact force. This is 65%, and this would be at 48% of your system pressure drop, or as close to these as you could get within the constraints. So choosing a TFA, combined TFA and flow rate, somewhere between these two lines would optimize you pretty much for hydraulic horsepower and also for your impact force as well. So that's how you would use a calculation for impact force and hydraulic horsepower. Somewhere in here is your optimum cleaning ability, basically. And if you can clean well, you can maximize your ROP as well. The roller cone applications requiring maximization of flow rate rather than hydraulic horsepower, as I mentioned before, sometimes optimizing flow rate's better than optimizing your hydraulic horsepower. The occasions when you might like to do that are when you're in soft formations where a high ROP is expected. Because if your ROP is very high, you're going to generate a whole lot of cuttings. So you really want to get those cuttings traveling up the hole as fast as you can, get them away from the bit. So you want to maximize your flow rate. So if you're in a soft formation where you're going to be drilling very, very fast, just get the flow rate up there. Forget about trying to optimize your hydraulic horsepower. And also in larger diameter holes, like greater than 12¼ inch hole, where soft steel inserts are in use. Again, this is like, when you're drilling fairly soft stuff where you might actually drill quite fast, but you've also got a larger diameter requiring, with lower annular velocity. So get the flow rate up to increase the annular velocity to get the cuttings out, rather than trying to optimize hydraulic horsepower in greater than 12¼ inch holes. And then applications which require a large cone offset. Cone offset is determined by how, the application, whether if it's got a large cone offset, it's usually, rather than just rolling, it's going to be rolling and dragging, and it's usually designed for a fairly soft formation. So again, it's just soft formations. If you've got a large cone offset, or if you've got high ROP, if your hole diameter is large, then don't go for optimizing your hydraulic horsepower. Go for maximizing the flow rate to get the cuttings out as quickly as you can. Get them traveling up the wellbore. Now, when you're using a PDC bit, the approach to optimization depends totally on mud type. Is it a water-based mud, or is it an oil-based mud, or an invert emulsion? If it's an oil-based mud, the penetration rate varies with the flow rate. For a PDC, this is fairly true. The penetration rate does vary with the flow rate. That's generally accepted. Therefore, flow rate should be maximized when you're using a PDC with oil-based mud. However, maximization of that flow rate should also be limited by the following considerations. The same considerations we've been talking about all the way through this. You've got to stay below your maximum standpipe pressure limit, which is probably 80%, as I said before, of the manufacturer's manufacturer's pump pressure limit. And you have to maintain a hydraulic horsepower per square inch, an HSI of between 1.5 to 2. The high ends for softer shales and clays and limestones as well. And you've got to keep but you've also got to, as well as doing these two things, you've also got to keep your annular velocity high enough for hole cleaning, but not so high as to wash out the looser formations. So you've got three different things there, and you've got to find a balance between them. If you go for one thing only, like maximizing your flow rate, you might lose out a little bit on your HSI, and you need to have a little bit of hydraulic horsepower per square inch. You need to have an optimum hydraulic horsepower per square inch to clean your bit, as well as keeping your annular velocity up there to clean the hole. So there's a bit of a trade-off here. Now, if you're using a PDC bit with water-based mud rather than oil-based mud, the bit can't be cleaned as efficiently as it can with oil-based mud. Remember back to I was talking about mud types, and diamond is oil wettable rather than water wettable. So the oil tends to coat diamond better than water does, and it also cools it very well for that reason as well. But the Oil-based mud tends to coat the cuttings and the steel, so there's a lot of lubricity involved, so the cuttings don't tend to cling to the bit. In water-based mud, the cuttings will tend to swell slightly, despite inhibition. And also, if you're in a swelling clay, then that will tend to adhere to the steel of the bit. It's very difficult to get. It's difficult to clean it efficiently. Therefore, your hydraulic horsepower per square inch needs to be increased to maximize the power used for cleaning the surface of the bit, rather than cleaning the wellbore. So here, if you're using water-based mud with a PDC bit, you've got to maximize that HSI, and that may involve limiting your flow rate a little, which means that you may end up having to limit your ROP a little so that you can clean the hole efficiently. So there's again a trade-off. Water-based mud may be less expensive, but you may need more rig time to drill the section with water-based mud. And again, if you spend a lot of time drilling a section with water-based mud, you may end up actually with reaction with the formation and so on, and having to do remedial action. So there's a lot of things to be thinking about when you're optimizing hydraulics and optimizing bit hydraulics. It's not just a case of plotting these graphs and saying, right, well, we'll just choose this TFA. You've got to start thinking about the pressures involved, whether you're going to be able to clean the hole, what type of mud you're using, everything. And in this case, with water-based mud, an HSI of around 5 should be aimed for within the maximum standpipe pressure constraints. So that's quite different to the 1.5 to 2 for oil-based mud. So in conclusion then, the overall hydraulics program, it must really optimize each of the circulating system variables, like pump speed, pump pressure, mud viscosity. You've got to optimize your rheology, and also the TFA as well, you know, your total flow area of the bit. You've got to optimize all of these variables to optimize the overall hydraulics program. You can't just optimize one and then hope that all the others will follow. When you optimize one, there's a trade-off with the others. So you've got to think about what's most important for your application. These 4 variables there actually control the flow rate, which is Q, and also then the annular velocity. And they also control the work done at the bit, the transference of energy from your surface system to the bit. So you're controlling the energy use at the bit, and you're also controlling the annular velocity and the hole cleaning ability. And so I hope it's made it clear, although we've got the option to optimize your hydraulic horsepower and your impact force, that's not always the answer. We can plot these graphs, but this is not always the answer, since we've got to actually consider the limits of the system, including the hole cleaning, the stability, the fracture gradient, the pump limits, everything else. Okay, so you're now able to basically list the components of the circulating system, appreciate the relative size of the pressure drops through each section of that system, know how the pressure is actually developed in the system, and also what effect you're going to have on the overall pressure drop in the system by changing some of the variables in each of these small sections. Things like pipe diameter, nozzle size, and so on. And then you should be able to understand what considerations go into optimization of hydraulics and bit hydraulics in particular.